So, let's start. Good afternoon. Thank you for your homeworks. Thank you for submission in time. Today we will talk about thermodynamics again, but something more important. It's called Carnot circle, and yeah, you will enjoy that. So, these homeworks were the first. We will finish next time the thermodynamics, and I will give you new one. And of course, I will correct and grade your homeworks as soon as possible. I will upload the fancy Excel table, and I will also upload the solutions. And when the midterm exam time will come, I will give you very similar or almost the same exercises with different numbers. I hope you had no difficulties to solve these homeworks. We didn't have time to fix all type of these exercises. We will see. Okay, so third time, the proposed midterm exam date is 11th of May. Retake is 19th of May. I just tell you because they say I have to tell you at least 3 times, and then you will note dates. So where we are, you are expert of mechanics, classical mechanics, oscillations including waves, acoustics, everything. I'm a bit sarcastic because in 3 weeks I told you everything about mechanics. So now we are in thermodynamics 3. Last time we talked about temperature scales, thermal expansions, different laws, ideal gas. Last time we talked about expansion work, internal energy. Now we will continue with cyclic processes, Carnot cycle, Carnot theorem, reduced state entropy, the second law of thermodynamics. Okay, let's see. What's this? Let's start with this. So, you can enjoy the larger resolution. I'm very happy. I always learn something. I always put this VGA connector to my plug to my slot, and you enjoy the much lower resolution. It's full HD. So what you can see is this PV diagram. And there is something, a circle. It's an ideal gas. You increase the pressure, expand it, decrease the pressure, then return to the original point. And this is called thermodynamic circle because the matter, the substance, return to the state after the successive process of changing state. You are very familiar with this. All engines, steam engine, car engine, everything is working in the same way. Even nuclear power plants, if you leave the nuclear reactor, then you have this, this cycle. This ideal gas got some heat, does some work, or just gives heat, or someone will do work on it. Doesn't matter. It's the same. So you return to the same state. I made this image with the Gemini. I just discovered how to do now fancy images with the artificial intelligence. It's much faster and more legal than just download an image and add the credit. Okay, that's next. There is something that's called efficiency. Efficiency means you give some energy and how much work you got. Actually, it is written right here, the work done by the system and the heat that you give to the system. This ratio gives the efficiency. There will be a formula for this later. This one. I will explain you, and during the practice we will work with this. I'm not 100% sure that this way how I deduct these formulas are the best to explain you the system. So, this is the same. There are heat that was absorbed, some heat was released. The difference and the full absorbed heat gives the efficiency of this circle. I mean this circle. Perhaps I should have put them in one slide, but at least you can understand. Welcome. Okay, Cornell circle. I'm not very good in French pronunciation, but I get the T is not pronounced. Saint Nicholas Rauna Carnot. First I read Soda, but it's a different guy. But this is the most this one and this one. These are red. It's red. Okay, Okay, so this is a term, and this is a term. I show you, these are red. It is just an optical illusion that you see it's black. So what you can see, we have a PV diagram, and we have an ideal gas. And this is a full circle. This drop line and this drag line is so these are isotherm lines. The temperature are the same, so you have this hyperbola actually. This is this red from the 1 to the 2. And also from the 3 to the 4, you can see the arrows. During this expansion, that's isothermal expansion, heat is given to the system from 1 to 2, and from 3 to 4, the heat is given from the system to the surrounding environment. The blue arrows that you can see, I mean the blue stuff, those are adiabata. Those are adiabatic processes. It means that the heat, there is no heat exchange. It's too fast, it's too large, or it's isolated. Doesn't matter. So the full cycle says isotherm, adiabatic, isotherm, adiabatic. That's a cycle. That's the Carnot cycle. This is the spirit, the mean, the essential of all engines. Okay, so from here, this 1, 2, we have an isothermal process. The T will not change, only the volume. So you got this amount of work. In the adiabatic part, you got this part. There is no heat exchange. On the isothermal part, you got this part. You can deduct this from the processes and the formulas given you last and the previous lectures. You can calculate also the efficiency, absorbed heat, released heat, absorbed heat. This comes from the work, the absorbed heat, and everything comes from here. You just write down and put here. If you use these adiabatic formulas and put them here, after a while you got this one. And this is important. The efficiency of the system is 1 minus TC TH. It means okay, this is important. I think this is the most important formula of today. You have a nuclear power plant, Paksh. The nuclear power plant in Paksh use pressurized water as for cooling. Let's say the temperature of the water is 327 Celsius degree, 600 Kelvin degree. The temperature outside is 27 degree, it's 300 K. If you use this formula, then you got that the efficiency is 50%. Something is not good. It's too high. Oh, I was wrong. Okay, I'm happy. Great. So this formula is okay. I thought there's a mistake in it because usually I got lower numbers. So what I told you. Oh, welcome.
Sorry.
No problem. Oh no, that is. So the efficiency of a nuclear power plant, I mean the Box nuclear power plant is 50%. S Carnot cycle. There are other nuclear reactors, experimental reactors, where the temperature could be 900 Celsius degree. But here we have this temperature. At this temperature, the water is pressurized. I'm not 100% sure, but it is far beyond the critical point. So the water is neither liquid nor gas. If you use natrium, for example, in the nuclear reactors of aircraft carriers or submarines, then you got a massive risk because the natrium is a very reactive sodium. natrium in Hungarian, sodium in English. The sodium is a very reactive element, but the temperature of the core could be much higher. So if you have a cool power plant, then the temperature is inside is 927 Celsius. The cold part, the environment, is 27 Celsius. Then the efficiency, Okay, why I give you these examples? Not because I don't suppose that you cannot understand this formula. I just want to teach you something. The engines, the cooled power plant, or I don't know what is the temperature in a engine, diesel engine or in a motor. So if there is 900 degree, then the efficiency could be 75%, could be. The nuclear power plant's efficiency is low. That's U, it's 50%. That's why you need a big river, at least in Hungary, or if you are in France, then you have these cooling towers, when condensation towers, and you need plenty of water to heat them because the heat loss is high. The biggest pollution of the nuclear power plant in Hungary is this heat pollution. I was born 80 kilometers south from the nuclear power plant. Some classmates told me that's why I'm Yeti and my soul is hairy and so on, but I assure you I'm not Han Solo, it's not the truth. But close to my place where I was born, there is a forest, and it was full of fishes. And now the fishes cannot breathe because they need a certain temperature to breathe, and the nuclear power plant changed it. Nowadays, our beloved government had a new rule. We have heat waves during the summer. And many times the surface temperature of the Danube is more than 30 Celsius degree. So they told that temporarily it could be higher. Then when the 30 Celsius degree is reached, then the nuclear power plant capacity should be decreased because of the heat pollution. But they changed the rules, and now they don't need to switch it off or decrease the power, the capacity of the nuclear power plants, reactors. Actually, the normal way in a normal country would be to build some extra condensation tower because the climate changed a little bit and they need this facility. Plockh 2, there is an extension of the nuclear power plant, will have condensation towers. And yes, okay, that's it. And the future would be actually some experimental reactors which would have 90 or 1000 Celsius degree capacity. Actually, there is an old type of nuclear reactors, boiling reactors. Those boiling reactors didn't use pressurized water. They just really boiled the water at 100 Celsius. If you calculate the efficiency, that's something horrible. So it's something this is the boiling. Actually, boiling is at 100, but it's easier to calculate if I do this. So this efficiency is important. Can I help you?
Not really.
Okay. So that's why I talk about Carnot cycles. What else we have? You know the first law of thermodynamics. So all change of the inner energy of the system comes from heat and work. The second law of thermodynamics is something different. There is something, it's called entropy. Entropy is a number of the sorry? It's order, yes, it's not reversibility, so the complexity of the system somehow, the structure of the system. If there is a crystal, and the crystal, the molecules or atoms are in order, its entropy is less than a liquid, a melted crystal. So sugar, just a sugar in crystal form, or a sodium chloride salt, is more ordered and its entropy is less than its solution. So this quantity called entropy. And the second law of thermodynamics says this entropy will not decrease. It always increases. However, I can tell you, because we are in 2026, so there were different approach. These guys, Max Planck, Oswald, Thomson, are the heroes of the classical physics. Max Planck actually also a hero, a very good scientist of quantum mechanics, and they gave different definitions. Heat energy does not spontaneously flow from a lower temperature body to a higher temperature body without any other changes occurring. Great. Yes, he noticed that the heat comes from the higher temperature to the lower temperature, but he didn't know why. Lord Kelvin. It is impossible to construct a device that operates in a circle and takes heat from a single reservoir and perform an equivalent amount of work without any other changes occurring. In other words, it is impossible to convert all the observed heat energy into work. This is actually how the engines and everything are working. There is always some loss of the heat. This formula gives actually heat. Max Planck. We are approaching these days. It is impossible to construct a machine that performs a work solely by the cooling of a single heat reservoir without any other processes. Such a machine is called second kind perpetual motion machine, perpetual mobile. There is no second second kind of type perpetual mobile. Oh, that's the last definition. If you are standing here and don't do anything, after a while you will see processes. The paintings on the wall are fainting. The cracks become larger, so the wall will drop. You will become older. Your world will grow. You will die and decompose. This is the natural way how the processes are going. The entropy must increase. There are some special cases when the entropy does not change or change very slowly. Okay. These circles, the thermodynamical circles, we are in ideal work, we use models, we have ideal gas, and this process is ideal, and it means also that's reservable. The process is reservable if after its occurrence, performing the process in the opposite direction with the system returns its original state through the same intermediate states without any other environmental changes. The process is irreversible if it is not reversible, meaning it cannot be resolved. If the system cannot pass through the same intermediate states in the reverse direction without any change occurring in its surroundings. In the real world, all processes are irreversible. The irreversible processes mentioned so far can be resolved. The internal combustion engines are irreversible. So we are dealing usually irreversible circles, but we say they are reservable. Why do we do this? Because it's easier to calculate. The model will work. So we have heat, the heat that we gave, the heat that prepared, and in this Carnot theorem, the efficiency can achieve this formula. Sorry for the different indexes, but usually they don't reach. So I just told you, okay, the efficiency of this engine is 75%, but in real world it's 71 or 60 or whatever. Yes. Okay. If we start from there and modify this formula, do this stuff. If the Q1, the heat which is given, is larger than 0, then we got finally this formula, which does not mean anything for you in this moment. But if I roll down, then I got this quantity called reduced heat. We have the heat and it is divided by temperature, like here. If I do the following thing, I have this generalized circle, thermodynamical circle, and I take and cut this circle to many small corner circles, then I have plenty of reduced heat and I can do this summary. And now we are in trouble. You are expert in integration. Perhaps you have learned integration. What about this one? What about multiple integrals? Two parameters, integrating one parameter, two parameter, three parameter. Gauss-Rogowski formula and Stokes equation. Don't worry, it is the material of fourth or sixth semester. Well, it's longer than your studies. I have to stop. Sorry. Yes, contour integration. Try to explain you what's this. That's nice and nicer. Are you familiar in complex numbers? Yes, okay, great. Okay, I have to look for something simpler. Okay, this is okay. This is more difficult than I thought. We learned about no. There is one integral. One integral is just a sum. If you have multiple integral, then you have two parameters, and you can calculate the surface of a planar object. If you have three integrals, three parameters, then the volume can be calculated. That's one thing. And that's the simple thing. However, it could be that the function that you integrate is not a scalar function. Its values are vectors. For example, you are in the magnetic field, you have a loop from metal, and move the loop. Then you generate currents in the loop. Then you can calculate this current with a special way of integration. The integration, the summary is go through the loop. You give a function for this, and then you somehow transfer it and transform it two-parameter integral somehow. If you don't understand, not a problem. I mean, the problem is not on your side. It's too early to give you, and I would need much more time to explain it properly. 2 or 3 semesters. It's enough usually. I learned it in the first semester a long time ago. Okay. Here, the meaning of this. You do not calculate the integrate below of this circle, like usually. You have a parameter which go through along this circle, and you calculate the amount and everything along this parameter. It's like the work. You have an orbit, you have a vector called force, and the work is the result of integration of the force along the orbit. For mathematics. Here we have the same, and we calculate everything along this Carnot circle on this. Looks back, but trust me, it's red, blue, red, and blue circle. This is what this circle or contour integrate means. Sorry about that. This is not a proper stuff, and perhaps I have told you without suitable mathematical knowledge, higher mathematical knowledge, I just can repeat the secondary school's material more or less. However, I have this quantity. It's called Clausius inequality, doesn't matter, reservable surface, irreservable surface, doesn't matter. I have this quantity, but not this quantity is important, but this one. If I have this quantity, change in the heat at a certain temperature, it's called entropy. And its unit is not written here, but it's joule per Kelvin. And this is the quantity that cannot be decreased. It is equal in certain cases at 0, Kelvin or something like this, or it increases. Yes, you can do also just normal integral, you can do a lot of things. You have this entropy right now. And this is the second law of thermodynamics for irresolvable circles. Irresolvable circles, there is equal sign here. Yeah. If you have a closed thermodynamic system, when closed means heat would be changed but the particle cannot, then this is the second law of thermodynamics. Change of entropy is quantity of irresolvability. If you have a system, for example, there is a tank, a glass, and there is water and ice in it, then the entropy is it has a number for the water and the number for the ice. After a while, if there is, it could be a closed system, it could be an open system, it could let it be a closed system, and there will be much more water than ice. After a while, the ice will melt. The order of the ice, the nice structure of the crystal, the water molecules crystal, will disappear. So the entropy will increase. This is a normal way of things. You cannot see that you have a water and then a certain temperature, of course, not zero temperature, but for example, higher temperature and appropriate, for example, 1 atmosphere pressure. You cannot see that, okay, we have ice and then it came from the water. No, the normal way is from the ice to water, so the melting is the normal. And when you have the system without ice and you have water, then you have the maximum entropy of the system, and this is the equilibrium state. Is this familiar from secondary school or somewhere? Entropy? I remember entropy from secondary school. Okay. My thermodynamics in second semester was about learning how to use partial derivation, because there were plenty of different parameters which describe the system. Entropy, enthalpy, heat, work, and so on and so on. Here we just have some of them. This is the first law of thermodynamics. The change of the inner energy of the system comes from the heat given to the system and the work. This work could be done on the system, or the system could do it on the environment. This is the normal way at constant pressure of the work. We have this definition for the entropy from here. We just change the T, went to the other side. And we can do the following. This goes here, and then I have this delta Q, but this delta Q, the heat, is less or equal to this TdS. So from here, moving to here, and then considering this one, we got this equation. After moving this side, I mean the right side to the left side, we got this equation. If the volume is constant and the temperature is also constant, then the change of the volume and the change of the temperature is zero. That's the reality, okay? Then this disappears because the dV, the change of the volume, is zero. The T will not change, that's okay. So I will have this one. So I will have this one. I will have this one. Here, we do again the same thing like last time. dt was 0. So this was this. So you have to think in the opposite direction to get this one. If you have something, deduction, the best thing that you can do to calculate yourself, to write it down and do it until you can do it by heart. You don't learn the formulas, you don't learn the science, you learn how to do the calculation. For example, this is one trick. This is a derivation actually, but if you just look here, you can look for a while until you understand what's going here. That's a trick. Okay, so there is a mistake here. I will correct this. This is not equal. This is L equal, so it's enjoy luck. Ta-da! So I corrected it right now. Okay. Yes. Here, there's a new definition, free energy. The sign is F. The unit is joule. It comes from the inner energy minus temperature multiplied by the entropy. So if you want, you can write at constant volume and constant temperature the second law of thermodynamics in this form, and you can deduct this form at constant volume and constant temperature. You always have to check whether what process you have. Is it isotherm, isochore, isobar, adiabatic, whatever. There are functions in thermodynamics. The enthalpy, inner energy, this is the work. You have free energy, and we have free enthalpy, but I did not define, but doesn't matter. Here you are. It's nice. Don't worry, if you lost, we are not the only one. I also lost when I learned it. I was happy to learn everything for the exam and for the committee exam later, and now I use usually the entropy if I use one of these. And this is a repeat from the last lecture. We have the P, the pressure volume diagram. This is the isochoric process, this is the isobar process, isothermal, and adiabatic process. And that's it. And this is not simple. Because I don't want to fail the full company, actually. Yeah, actually there is something weird. We started the semester with 16 students, and now we are 19. So I don't know what you have done, but you are more right now. It's a bit weird, but okay. I had something similar. I taught 30 students at the University of Cambridge, and after 1 month I recognized there are 60 students in the same group. They just come. So they got the visa and joined us. But you are in the second semester, so this cannot be the explanation. Okay, what do you think about this? It's not quantum gravitation theory, but there are a lot of things that you can miss. What is familiar from this? Carnot cycle, is it familiar? I remember from secondary school Carnot cycle, and I remember this 1 minus T1 per T2 formula. This plot is not the nicest, but correct. The AI calculated me this figure correctly, and then I had to modify a lot of things, but the curves are fine. The entropy always growing or 0, but usually it's increasing. reduce speed. I could not write and or find a better plot than this one, so we use this one. This is the normal thermal cycle, and it is divided into a lot of small common cycles. Great. And we have free energy. Let me check what's this free enthalpy. Oops. No, it's practice. One call. Enthalpy, yes. We have enthalpy, that's fine. We have enthalpy, that's great. They go up. Okay, it is not written anywhere that this enthalpy or free energy, free enthalpy. So I think you can live without it, or I can give this somewhere that is nothing more than enthalpy minus Ts, and the temperature minus enthalpy. So, I think we should stop for we should have a break and then continue with the calculations.